Hello, SciPy 2020. I'm Simon, and today I'll talk about machine learning model serving. I'll give you an overview of what serving machine learning models mean and why it requires. After this talk, I hope you can take away with some understanding of the model serving landscape, learn common approaches and people, and learn about a new library I've been developing to overcome the common pain points. So who am I? I'm a software engineer working at an early-stage startup called Aniscale, and Aniscale is a company behind Ray, which is a fast and simple framework for building and running distributed applications. At Aniscale, we work on to make it possible to program your cluster as easy as your laptop. I actively contribute to several open-source software around machine learning, distributed data processing, and model serving in Python. Let's start with what is model serving or model inference, or some people call it prediction serving. In particular, where does it fit into the machine learning lifecycle? To build and deploy machine learning power applications, we roughly have these three major steps. You first develop the model, and then you train the model, and then you perform inference on the model. Model development is where we collect the data, analyze the data, and iteratively improve the model. Once we have the model, it is pushed into a training pipeline that learns from live production data. And what happens then, after we have several hundred trained or even validated models, these models need to be put inside a prediction service suitable for end user application. And the last stage, the inference stage, is what we care about when we're talking about serving machine learning model and deploy to production. So this talk will be structured as follows. I'll first discuss some requirements for model serving to get some overview of what a typical model serving workload looks like. And then I'll talk about two common approaches for model serving. These two common approaches roughly covers all the current model serving solution out there. And lastly, I'll introduce RayServe, which is a framework built on top of distributed runtime Ray and make it easy for serving machine learning model, scaling them to many machines while delivering end-to-end control over the prediction. Let's start with the requirements and what are some basic requirements for model servers. So I listed 7 of them, and there are definitely more. So let's start with the basic one. Well, first of all, it needs to deliver predictions. Given an input, right here, we have a cat, and you should run through the machine learning model and output the prediction, it's a cat. But in many cases, we have more than just one type of model. There is a need to multiplex different models. Regardless of different versions, different algorithms, or even different model architecture, it is more than practical to use different models for even the same problem. Different frameworks each have their pros and cons and specialties. To solve a real-world problem, we just need to grab the best tools available out there, and then model servers should take care of multiplexing among different models. Another key characteristics of machine learning models is that they're quite slow and resource intensive. We don't want the user to wait for the request to pile up. What can we do? Model servers should be able to transparently scale the model to multiple replicas and no balance among them, so requests can be parallelized. Despite being resource intensive and often slow, a machine learning model can actually utilize hardware parallelism like vectorizing instruction, multi-threading to efficiently perform inference on a batch of requests. Many times, performing inference on a batch of, say, 4 images only come with a very small, negligible cost compared to, say, just performing a batch of 1 image. Batching is a very simple technique to improve your hardware utilization and improve the throughput of the model. And when you put the model in production, we often want to periodically retrain the model on fresh data and experiment with different hyperparameters. This is when versioning becomes an important requirement. Can the serving system enable zero downtime deployment? gradual rollout and rollback, or A/B testing. Can we transparently update the version of the model and test the new version without any user notice any difference? And then there's also requirements for handling pre-processing and post-processing logic for the models. Typically, our models accept numeric tensors and output numeric tensors. But this is not what end users want. For the model, they expect validated and transformed inputs. The output array of floating points and numbers means nothing to the user of the machine learning applications. So therefore, pre-processing and post-processing logic is critical to ML model servers. And then last but not least, we need to pay attention to how much performance we're getting out of the hardware and their relative cost. Because machine learning models are computationally expensive, their relative throughput is low. To handle large volume of incoming data, we need to trade off cost, performance, latency, and throughput. Does your serving system allow you to tweak this parameter? Does your serving system help you optimize your cost given your performance requirements? So in summary, serving machine learning model has sort of its unique set of requirements. Let's actually take a look at how people deploy models in production today. So there are two common approaches to deploy models in production. I'll discuss them one by one. One approach is to embed your model evaluation logic inside any web server. The second approach is to offload the model prediction to an external specialized service. Let's take a look at the first approach. The first approach typically wraps the model inside a conventional web server. I'll use Flask, a popular Python web framework, as an example here. When HTTP requests come in, the Flask server can dispatch the request to different API endpoints. We can make one of these endpoint handler to handle our model evaluation. Let's say we reach /API image predict endpoint. The input will be transformed and evaluated in the TensorFlow models. The output result is captured inside the return response. And there we can have a very basic model servers. Let's take a look at some pros and cons of this approach. The web server approach is simple and easy to build and easy to understand. It gives the developer end-to-end control over how the request is handled and how the model is served. If you're just doing simple demo or proof of concept, this approach is perfect because it gets the job done. However, a big downside of this approach happens whenever you want to scale more than one query at a time or have multiple models to be served at the same time. And the model is typically loaded on some sort of global variable, and there's no way to manage the startup, initialization, weight loading, and other lifecycle of the model. And lastly, if one of these model crashes, it can bring down the whole web server. And there are actually a few more hurdles to jump through with this kind of approach. A typical deployment for Python web servers are process pool based. This means requests are load balanced across different instantiation of the worker processes. And as we discussed above, a model is typically stored as a global variable, and there's no control over the loading of the model. What happens when we say have 3 different models for the web server? Let's take a closer look. So we put 3 models for our web server, and then using this kind of process pool-based deployment mechanism, 3 models can quickly get turned into tens of models. And then without any additional optimization, a typical deployment will often encounter a memory issue. And that's not just it. Another issue with this kind of web server approach is that it's difficult to form inference pipeline. What do I mean by that? Let's say one of this kind of circle represents a machine learning model. In a typical user-facing machine learning powered application, models don't work in isolation. Typically, there's a chain of operators that involves pre-process and post-processing. And there are other cases where we first need to do embedding lookup or input data featureization. There are also cases where we need to split the request to different models to perform A/B testing. For example, we want to send 80% of the traffic to one of the model, and then the other 20% to the other model. And that's not just it. There are also cases we can use ensemble as a technique to improve accuracy of the prediction. So the ensemble means combining output from different models, either through, say, averaging or voting their classification results. And this can help combat model biases and also improve the accuracy. There are more advanced techniques like cascade. For example, to optimize the end-to-end latency of a given query, we can first try to run the model, run the input on a faster and simpler model. And only if the model outputs a low confidence, we route the input to a heavier weight, but more accurate model. Otherwise, given this high confidence of the output, we can just return the results from the faster model. So in summary, a simple web server is great for demos or proof of concepts. They actually require a lot of optimization to make it production ready. When just a simple web server is not enough, people turn to the second approach. That is, offload the prediction to a specialized external services. Using our previous Flask example, the /API image predict endpoint, when you receive the request, instead of passing it through TensorFlow, it will now forward the request to some sort of external services, here represented in the cloud. This kind of services, there are many out there. So some example includes like TensorServing from Google, Onyx Runtime from Facebook and Microsoft, Seldom, TensorRT from NVIDIA, and AWS SageMaker. Let's actually take a step back and examine this approach. When requests come in through HTTP, there are many steps before it reaches the model for the core inference logic, and many steps actually after the inference logic. When an HTTP request comes in, it needs to be checked and validated, and it needs to be parsed and transformed with custom business logic specific to the workload. And then we need to transform the input such that it can be run by the model. And then after we run the model, we also need to transform the model output with custom business logic, and then finally turn into HTTP response. So what happened when we have external service? Originally, the entire stack of these kind of steps happen in the web browser. When we add the external service, the sort of inference step got shipped to the external service. And only the inference step, the input-output transformation, sort of span across different the web server and external services. I will also characterize these kind of approach like the external services as tensor-in, tensor-out, because their interface is pretty limited to just numeric tensors or some variant of it. So as a concrete example, if we want to perform image prediction classification, we need to take in bytes from API request, JPEG decode it, and then do some maybe color normalization, image resizing, cropping, and then convert it to 3D RGB numeric arrays. And then this is the point when we ship the sort of 3D numeric arrays to the inference stage, to the external service. And then when the external service outputs some the model prediction output, that's also numeric tensors. And then back in the web server, we need to translate the output to English labels or database IDs. It is worth noting that some of these logic are tightly coupled with the model itself. So if we update the model step, we might actually need to update the pre-processing or post-processing as well. And additionally, the split between one part of the request handling logic and the other part of this kind of model inference logic really just brings a lot of operational complexity. So in summary, external service approach encourages separation of concern, but it sort of lets you have to manage different services separately and tune them separately. And then model evaluation logic are now split from core business logic. Changes in one place need to be closely checked and sort of mirrored to the other part as well. And this approach is hard to learn because now you have to learn sort of new APIs and new custom systems. And they're also hard to debug because now it's no longer just inside a single process, and then it's no longer you are tuning using your original training framework as you are familiar with. You now have to deal with RPCs. You now have to check in like external service configuration, encoding, decoding, and even encryptions. And then think about how you deploy the models and tune the model. Is there a better way? So we built Reserve. Reserve leveraged the RAID system to easily and transparently scale the model to 100 cores. And then it also gives end-to-end control of how the request is handled. And then just like the web server, but like we sort of put the model in isolated components and we scale each model independently. Reserve takes care of load balancing among different model replicas. And Reserve is also pipeline native. We enable user to easily combine multiple models and easily construct and connect models in Python. Reserve has built-in extensibility. We call it a programmable serving system that allows you to modify how it works while it's running. We also offer monitoring and observability tool out of the box. Let's actually take a closer look at the Reserve API. Model can be defined with simple Python classes. The model can be loaded in the init method. You can add any member method as you like. The call method identifies an HTTP request handler. The Reserve exposes a Flask request interface, so it's easy to use, easy to understand, and easy to migrate your existing demo or proof of concept application. You can add arbitrary business logic, pre-processing, or post-processing to this handler. The key is that model evaluation and its surrounding business logic are now in one place. Reserve has a concept of backends and endpoints. A backend is associated with the model implementation, and it's versioned and it's scalable. For example, you can specify the number of replica in the query backend. An endpoint is a user-reachable endpoint that's associated with the HTTP route, as well as it can be connected with multiple backends. Let's take a closer look. So endpoints, in a way, is a logical service. It can be reached by URL, and it can be mapped to multiple backends. Backends are versioned models. So under an endpoint, you can associate the endpoint with different backends, which are their own scalable implementation. On the illustration to the right, we're showing the endpoint/API, which is what user will call. And then the incoming requests are actually split across different backends. And each of these backends actually have different numbers of replicas, and they can be managed separately and scaled separately. And Reserve had composing, this kind of built-in support for composing models together. In Reserve, in your backend implementation, you can directly invoke queries or invoke methods on the endpoint. Instead of configuring your services with YAML, Reserve's configuration language is just Python. It is a language you are familiar with, and this is a language we'll use for you to configure the running system. And because we're built on top of RAID, the distributed runtime that allows us to update the running cluster and make every single component fully fault tolerant. When a component goes down, RAID can automatically restart it and connect it with other components. And Reserve is just a Python package, so you can run it on your laptop for quick demo and development. And then you can deploy it to a server. It also provides built-in template for you to run on Reserve on Kubernetes, as well as all the major public cloud. You can try it out today by just pip install and import from Ray import serve. We have a vibrant community discussing Reserve in the Ray Slack. You can also check out the documentation in docs.ray.io. Also, we recently published several blog posts about Reserve, including a write-up version of this talk in our Medium page. Please check it out. And then lastly, the key takeaway for this talk. There are two common approaches to model serving. One is to just wrap your model in a web server. And the other approach is sort of this kind of offload prediction to a tensor-in, tensor-out system. And both of these approaches have their own flaws. Reserve is a web framework that bridges the benefits of these two approaches. It can help you to scale model to many machines, while grants the data scientist the ability to sort of and the end-to-end control over what their machine learning APIs. And that's it for the talk. And I hope you learned something. Thank you.